Awesome. Well, Quinn showed me. He showed me one. He saw me in the hall, and he was like, "Got something to show you." I'm like, "Oh yeah, yeah." All right. Let's go ahead and get started. Let's see. So, a couple things. Before I pass out homework 6, I want everybody to be clear on the schedule. I'm going to make it a habit to have this on every slide from here on out. So this is our homework schedule for the rest of the semester. And as far as I know, we should maintain it. We're doing good on time and coverage of topics. So you all have homework 7 in hand right now. It is due on the 14th. Now, because I'm aware that when you're using the alignment charts, you have a tendency maybe to draw a line on it, and between all the examples we've done in class and what have you, it might be kind of covered and tough to interpret. So if you go on to, or if you go to the huddle station right outside my office, I got a big pile of them. So if you want to grab a couple, that's fine. So, and when we have the exam, I'll have a fresh one on the exam for you. So, sound good?
Do we need to mark on them for the homework?
You don't have to, no, but I'm just saying if you have inadvertently done so during class or for, let's say, for problem 1, because problem 1 you have to do like 6 of them, so I wanted to make sure you had extras. Sound good? Okay, so again, from here on out, homework is going to be assigned each Friday and due each Friday to sort of get through our topics. I could combine homeworks 8 and 9 into a single beam homework, but that would be a really big homework. So, yes. Not quite. Not quite. I just needed to trim. So it's starting to get warm again, is what it is. So
You already have that.
I could go the other way, right? I could go the other way, get the long hair again. I don't have the discipline to do that again, so that's the issue. All right. What's that? It was rough. Oh, you mean when you grew yours out? When you grew yours out? No, yeah, I could totally get along with it. See, for me, when my hair grew out, it was very, very straight. So when it got right here in my eyes, that was the tough spot. Mr. Chadwick. Let's see. Miss Clark. Mr. Conley. I'm sorry. I was like smacking you in the face with it. Oh, didn't mean for that to happen. Mr. Mays. Mr. Mitchell. That's I know. Mr. Morris. Mr. Schaffer.
We were all talking about tomorrow.
No. If you look at the symbols, there's one that matches where it's allowed to translate, but it's allowed to translate, but it's fixed from rotation. Yeah.
Oh, okay. Yeah, that's in the back of the book.
The one thing I do want to show you all a little bit on this homework is problem 1. I do want to spend some time on that because I know there were some odd plots. First off, your plot should have looked like this, okay? It should have had this sort of shape to it. And in terms of constructing the plot, a couple of things. Number 1, okay, if you go to your handouts and go to, I think it's column handout 2, I think it's this one. Yeah, and you look like right on the first page, I mean, there's your equations right there. So they were actually, I mean, it's literally right there. The only thing that this does not have is phi. You have to adjust it by 0.9. So let me show you how I did this. What I did is I have KL over R from 0 to 200 right here. And I have an elastic, or my Euler buckling capacity calculation. Now, at KL over R equals 0, you're dividing by 0, so it's essentially infinity. But it doesn't really matter. which means your F critical is 36. But the big thing I want to show you is this formula right here. So here's what this formula is saying. It's basically one big if-then statement. It's saying if your KL over R is less than or equal to 4.71 times the square root of 29,000 divided by Fy, whatever Fy is, then your capacity is 0.658 raised to the quantity Fy over Fe times Fy, or it's 0.877 times Fe. And that's it. And then just boop, copy and paste, just to make sure that, you know, when you do that, you're locking in your Fy, because that doesn't change. That's always 36. Or you could have a column just full of 36s. That wouldn't matter. Now, what that will give you is F critical. Phi F critical, you got to multiply it by 0.9. So when it's all said and done, you should have a plot that looks something like that, and that's essentially it. So that one, I think with a little bit of Excel creativity, was pretty straightforward. The advantage of doing it like this is if I go through and say, well, my yield stress is 42, the curve changes accordingly, you know. So, okay. Now for the rest of the solution, let's see. So I think the big thing was just making sure you're getting the right lookup values. Let's see, I think your KL over R for problem 2 ended up governing in the x-axis. It was about 110.3. That was your KL over R. So when you calculate your capacity using E3, you compare KL over R to 4.71 times the square root of E over Fy, and it is just on the other side of that. So you're still using your 0.658. You should get a capacity of around 266 kips. Now, if you use table 4.1, you end up getting 265.5. And that, again, that just comes from interpolation, just the fact that you're assuming it's a straight line. Again, you're assuming it's a straight line when you do interpolation, but it's not. You know, that's obviously not a straight line. Okay, so make sense? Okay, now on problem 3, a couple things. So here were my trial sections. I chose a 14 by 82, a 12 by 72, and a 10 by 88. Technically, I could have chosen the 10 by 77, but I think when you actually go through and choose that, I think you can look at it and see that's probably a close call, since its capacity is, in fact, exactly 720. So when you do your interpolation, you can probably make a guess and say it's not going to work. But I want to show you something. So let's take a look at this. So your KL in the x direction is 36 feet, and your KL in the y direction is 15 feet. Now, if you take each section one at a time, let's take the 14 by 82. So your Rx over Ry is 2.44. So if you calculate your KL effective, you get 14.75. Now, that value is less than this. Okay, and because it's less than this, you know that your weak axis governs, and whatever you looked up in that table is at the capacity. So I can tell you right now, without doing any more work, the W14 by 82 will work. It will be it will be one that works. Now, because the W14 by 82 works, I didn't even waste my time doing the W10 by 88. Because if the W14 by 82 works, why would I check one that's heavier? It'd just be wasting my time, because I know this one works. So my efforts from here on out are going to be on the W12 by 72. Now when I divide by Rx over Ry, I get 20.57. If you compare that against this, it tells you that the strong axis governs, so that means you need to do a little bit of interpolation. But when you look at the interpolation that you would do, you would be interpolating between, it's what, 20.57, so you got to look up the value for 20. And since there's no value for 21, you got to look up the value for 22. So you'd be interpolating somewhere between 602 and 547, and whatever the value is between 602 and 547, it's less than 720. So you don't need to do the interpolation here either. So the W14 by 82 works, the W12 by 72 doesn't work, and I didn't waste my time doing this one because it's heavier than that one. So my answer is the W14 by 82. Yes?
So how did you determine the K values on those?
Okay, let me see. was it this one? Actually, I think it was this one. Let me see. Nope, it wasn't this one. It was this one. Okay. All right. All right, first off, I can see where there would be some mix-ups there. I was trying to match the symbols that were on the homework exactly to the symbols that were in the manual. So if you notice, like that one column, it's not fixed. It has that block. Okay, do y'all see what I'm talking about? Okay. The difference between, like, if you look at column A versus column C, and actually, you know what? Let me pull it up in the slideshow because it's a little pixelated here. Was it slide 276? Okay. Here we go. The difference between, let's look at the difference between A and C. So if you notice, A is fixed, fixed, and C is kind of fixed, fixed. The difference between this boundary condition and this boundary condition is this boundary condition is allowed to move. It's not allowed to rotate, but it's allowed to move. See, I was using these in condition codes right here to draft out those symbols. Okay. So if you have a column that's fixed on the bottom, but the boundary condition on top is fixed against rotation but free to translate, that would be KC, and your K value would be 1.2. Does that make sense?
What's an example of that plastic boundary?
A moment frame, or something like a moment frame. Because a moment frame, I mean, what's the difference between a brace frame and a moment frame? A moment frame is allowed this way. But you are correct. If you were, let me say this, if you were actually doing a moment frame, you would probably end up using the alignment chart anyways. But to sort of, I guess, add a little bit of reality to it, when we did a lot of moment frame problems, we were getting K values like 1.2 and what have you. In fact, when you do your homework assignment, you probably are going to get K values around 1.2 for some of those columns. So, does that make sense? Does that answer your question? Anybody else? Again, I apologize if it was a little unclear. I tried to do my best to, literally, like if you look, like I'm literally using the same symbol, you know, like line for line to try and match it. So, sorry. Everybody okay? All right. Let me see. Does everybody have a copy of Homework 7? Because I still got some copies over here if you haven't grabbed them. Those are due Friday, so. Okay. All right. Now, what slide was I on? It was on like something like this. Something like this. Okay. Then let's get into the world of beams. Now, if you recall from last time, let me go back a little bit. I showed you all the greatest slide ever. I'm going to show you again. Yeah. So if you recall, if you have a beam and you apply some moment to it, it starts off behaving elastically, okay? And it will behave elastically until you reach the yield stress at either the top or the bottom of the section, assuming it's symmetric. Now, in mechanics of deformable bodies, that's where we essentially assumed that everything stopped. You know, once you reach some limiting stress at the extreme fibers, you're done. But in reality, that's not the maximum moment that a beam can withstand. Now, if you keep applying moment to this, what happens is, well, the very top and the very bottom have yielded, but that doesn't mean that this is yielded or that's yielded or any of these points in the middle. So once you keep applying moment, that yielding penetrates throughout the section to the point where you've yielded the entire cross-section, and that's the point that matters. We call that the plastic moment. Any excuse I have to show that slide again, I will, because that slide's awesome. Oh, whoops, sorry. And you do need the sign-in sheet. Okay. So, sign-in sheet and solutions to homework 6. It'd be messed up if one day I just said, you know what, no. No. say, you're on your own. 1, 2, 3, 4, 5, 6. Yeah, that's true. You can sit there and just pause the video. You can do it. Okay. All right. Let's get to it. Okay, so last time we did an example discussing plastic moment and a new section property that we discovered called ZX, okay? And ZX is essentially, it's a little bit different than, something like a section modulus. Elastic section properties and whatnot are defined based off the neutral axis, or where the centroid is. Whereas plastic section properties are more about where the area above a given line equals the area below, because we're talking about compression equals tension, and they're not necessarily in the same spot. If you go through and do the math, you'll find that in many cases the location of the centroid and the location of the plastic neutral axis are in two different spots. And I even mentioned this in tension members a while back. I said, we have Y bar and we have Y sub P. And I was like, when we were doing tension members, I said, don't use the Y sub P. Well, now you know why, because they're referring to different properties. And we did an example, something about like this, where we computed the location of the PNA, ZX, and ultimately the plastic moment. Now, if you go through and compute the centroid of this section, what do we get? We got like 5 inches, like up here, like that was this plastic neutral axis. Was it 5? Yep. Yeah. If you do the centroid, sum of AY over sum of A, it doesn't come out to be 5 inches. It's something like 7.5, 7.6, something like that. Because as you start yielding throughout the section, that neutral axis has to shift in order to maintain equilibrium. Okay. So far, so good? Okay. So now let's talk about beams. Let's talk about how to actually proportion them, analyze them, design them. In order to do this, this is going to be a discussion that we have for the rest of the semester. We're going to start off making an assumption that LB equals 0. Okay? Now, what's LB? Well, we mentioned this last time. LB is essentially the distance between bracing elements for a given beam. Okay? So, like with you have a column that was like, 30 foot long, but we really didn't care about the overall length of the column when we were determining capacity. We cared about the distance between unbraced segments, or the distance between bracing elements. So if we had a 30-foot long column, but there were simple braces every 10 feet, well, when we computed capacity, we just said the L was 10 feet. We didn't say it was 30, right? Same thing is true with beams. I think that it might be a little more confusing with beams because when you compute the forces, the moments, WL squared over 8, you're using the whole span length, but you might not be using that for the unbraced. So it's just something you got to make sure that you're paying attention to. Now, some examples of lateral bracing. Now, what I mean by lateral bracing is trying to prevent a beam from moving, to the left or right. So there's a couple examples of that. One of them might be something like this. If you have a composite slab, and you've got something like shear studs welded to the top flange, and then that slab is locked in with that beam, then that beam cannot move to the left or right at all. So the way that we would describe this is we would describe this beam as having continuous lateral support. So LB is the distance between braces. What we would say for a beam like this is that because it is continuously braced, we'd be saying LB is 0. Okay? Does that make sense? Everybody okay with that? Now, here's another example of lateral bracing. If you've got a floor system and you just have beams framing into one another. So, for instance, if I was looking at, like, let's say this girder, the span length of the girder might be something like 30 feet. But the unbraced length, the LB, might only be 10 feet because it might only be 10 feet from this beam to this beam. And those beams are preventing that girder from moving to the left or right. Okay? Does that make sense? Everybody okay with that? Okay. Another example, more common in bridge applications, is the use of a cross frame. So, for instance, you have some of these girders. Some of these girders might be 100 feet long or so. Like that girder there on the right might be a couple hundred feet long. but the unbraced length, the L sub B, might only be something like 20, 25 feet, because that's the distance between those braces. Those look like, inverted K-frames or something like that. On the image on the left, just X braces and what have you. Does that make sense? Anybody have any questions about this? This isn't too bad, right? The big thing is I just want you to understand the difference between how long a girder is and the distance between its braces, okay? And like I said, for the first component of this beam design stuff, we're going to be assuming L is 0, okay? And the reason why we're making that assumption is because we're assuming that there's no buckling going on. We're going to assume no buckling now, and then later we're going to ask, well, what if we did have to account for buckling, which is the case in a number of scenarios, and then we'll go into that. Okay. Everybody good so far? Okay. Now, if I'm designing a beam, I really have three things to consider. And I think those of you in concrete design or who have already had concrete design could probably spit this stuff out by now. If you're designing beams, we really have three things that we need to consider from a design standpoint. We have moment, we have shear, and we have deflections, right? I mean, when we design beams, that's essentially what we care about, that we had adequate moment strength, we had adequate shear strength, and that we had adequate serviceability considerations met. Sound good? Now, let me just say something real quick on shear, okay? Now, if you're designing something like a plate girder, let's say a plate girder in a bridge, and you've got like a really, really thin web on that girder, well, in that scenario, shear becomes a much bigger deal. And the design for shear is somewhat analogous to what we did in concrete design for stirrups. Instead of laying out a hooped rebar, piece of stirrup, we're laying out stiffeners. You all have probably driven down the road and seen maybe like an older steel bridge, and they've got those vertical plates on the web of the girder. That's what those vertical plates are doing. They're there to help the girder's capacity in shear. But I'll say for considerations, that's pretty rare. The way that we roll I shapes, the W30 by 90s and the W27 by 94s, etc., the webs come out pretty stocky, and for lack of a better term, you're going to find shear capacity not really a big issue. We're going to see problems where we'll have let's say 20 kips in shear and 120 kips in capacity. I mean, it's just going to blow it out of the water. Really what's going to govern our design is going to be flexure or moment, or moment and deflection, I guess I should say. Now, if you go to the spec, remember Chapter D is on tension members and Chapter E was on compression members. Y'all remember that? Well, Chapter F is going to be on flexure. Chapter G is going to be on shear, and Chapter L is going to be on deflections. We're really not going to actually look very much at Chapter L, but that'll become clear here in a second. Now, speaking of the manual, let's talk about some tabs. If you'll notice in this class, I never gave you all a beam design aid. I gave it to you in concrete design, but not in here. The reason why is it's in the manual. Okay, so if you open your manual, now this is page 3-something, so I'm in the front matter of the manual. If you go onto those gold tabs, the one that says beam, and I'm in pretty much the last chunk of that section on 3-213, you'll notice a table that says table 3-23, shears, moments, and deflections. And there's dozens of different scenarios and loading considerations, like for instance, case 1, a simple beam, uniformly distributed load, arguably the most common instance of a beam loading that we see in this. So maximum moment, WL squared over 8 at midspan, maximum shear, WL over 2, maximum deflection, 5WL to the 4th over 3, 40I. Those of you that are in concrete design right now, that stuff's got to be pretty familiar. So you know where that is. So the only thing I would just the only thing I would pay attention to is just make sure that you're paying attention to the and the variables going into it. Like if you're doing something with triangular loads, just make sure that you're using the right units and the right input to get the values that you're interested in. But other than that, this is a pretty straightforward guide and a really, really useful one. Sound good? Now, One thing I'll go on real quick about, if you remember with columns, concept of local buckling, maybe bless you. The idea is that instead of the whole column buckling, maybe it's just the flange that buckles, or maybe it's just the web that buckles. And you remember the way that we would check that is we would compare the slenderness, the BF over 2TF and the H over TW against certain limits. Well, it's the same thing with beams. The limits are a little more intricate, but for our purposes, it doesn't really matter, and I'll explain why. Beams, because of their behavior, instead of splitting them up into two categories, we split them up into three. So if you remember with columns, we either said that the elements are going to buckle or they're not going to buckle. And we would compare that against like a 0.56 square root of E over Fy or a 1.49 square root over Fy. With beams, we're a little more intricate with it. We say either beams aren't going to buckle locally, they're going to buckle locally in an inelastic fashion, or they're going to buckle locally in an elastic fashion. Only for our purposes, I don't think it really matters, because the long and short of it is this. If you go to 16.1-16, so I want everybody to go to that. You should have that tabbed already if you haven't already tabbed it. So that's this table right here, 16.1-16. I want everybody to turn to that. That one should be tabbed. I hope it's tabbed. They do not tab it.
I didn't tab. Okay, around it.
All right, 16.1-16. Okay, now if you look over here on the left, the table on the left should be very familiar. Y'all recognize this? That's the one for columns, right? Well, by golly gosh gee, look at the one on the right. The one on the right is for beams. Okay, you'll notice there's two limiting ratios, lambda sub p and lambda sub r. For our purposes in this class, we're only going to care about lambda sub p, and more often than not, all of our beams are going to meet these requirements. You will find some beams that don't meet these requirements. In other words, we do have local buckling considerations. Fortunately, a lot of the design guides we use take this into account. I want you all to at least check these on your homework problems, but it really shouldn't be a major concern. Sound good? Don't worry, we'll have some practice going into this. Sound good? All right. Okay. Now, if we are talking about a continuous braced beam, in other words, a beam where buckling isn't going to occur, then I propose that the capacity is just MP. It's plastic moment, right? And how do we compute MP? We take Fy and we multiply it by its Zx, right? It's plastic section modulus. Everybody okay with that? So here's the capacity of the beam in bending that isn't going to buckle. Fyzx. The phi value is 0.9, and this is going to be our capacity expression for the first beam component of this class, Fyzx. All right. Now, just real quick on units, when you calculate this out, Fy is in what? KSI, Zx is in cubic inches. So when you compute your moment, it's going to be in inch kips, right? So you need to make sure and divide by 12 to get foot kips. Sound good? All right. Now, I've had you all tab a couple things just now. If there's one thing I really, really want you to tab, it's this. It's table 2. We will use table 3-2 for the rest of the semester. So I want everybody to turn to table 3-2 right now. Okay, so here, it starts on 3-19. That isn't page 3-19. I think that's a page further into it. But it starts on page 3-19. That definitely needs to be tabbed. We will use that for the rest of the semester. Okay? Now, if you'll notice, there's a lot of information here. Yes? What? I'm confused. That's fine if you want to do that. Just it doesn't matter to me. I just want to make sure you can find it. I'm not. I was wondering if you were making a pun there or something. I'll just tell more pun jokes. Yeah, I'll just use more puns. Okay. Ow, now. Okay, I really want you all to pay attention to this table because there's a lot of stuff in this table, a lot of incredibly useful information in this table, okay? First off, okay, so this table, if you notice, it's called the ZX tables because the shapes are organized by their ZX. Like if you notice, the ZX values are going down. Like that's how they're organized, okay? So that's point one. Point two, you'll notice it lists, maybe if the mouse cursor was out of the way, it lists phi and p. Okay, now move the mouse. There we go. It lists phi and p. So that's what this is. Phi and p. Now it's called phi and px because it's the strong axis. That's all that means. Okay, so phi and p, it's listing it for allowable stress and LRFD. Okay, now there's a couple terms that you haven't been acquainted to yet. First off, phi MR, you don't know what that is yet. We will get to it. You don't know what these beam factors are. We will get to that. Okay. Also, LP and LR, we'll get to that later. These four terms are related to buckling, but we will get to that. Okay. It also lists moment of inertia, and just pop quick, what do you think the phi VN is? Shear capacity. So for now, we're just going to look it up. We'll talk at the very end how to compute shear capacity. It's just not going to be a big deal. Yes?
What are the bold sections and
That is a wonderful question. Okay, and if I am actually asking you all this question. So if you look at the sections and notice how they're broken up into chunks. Like there's like maybe 5 members and then 3 members and then 6 members and 4 members, and they're broken up into like rows, like 6-row chunks or 5-row chunks. Everybody see that? And notice how within each chunk, the top row is bolded. Why? Why is the top row bolded? Within a chunk. It's the lightest. Look right here on the slide. Notice this is from page 3 dash, I think it's 23. And if you notice, this chunk on the top is a 30 by 116 and 147, 131, 158, da, da, da. Of that group, that's the lightest, okay? Okay, look at this. Look at it. It's easier to see on 3-23. Turn to 3-23. Okay, so start at the 30-116, right? Now notice, every single shape in this table is listed according to ZX. That's number one. So I went into Excel and I just sorted it by ZX, okay? Now, look what happens. So 116, then 147, 131, 158, 193, 210. As soon as you see a section that's lighter than the 116, there's a space. Do you see that? Then the next section is what? The W30 by 108? And then it keeps going. And then once you find a section that's lighter than the 108, you put a space. Then once you see a section that's lighter than the 30 by 99, you put a space. Does that make sense? It's tougher to see on the first page because you're dealing with these super heavy sections that they're all designed to be that economical shape. So it's just those bold rows. Does that make sense? All right. So in terms of economy, you might be solving for a ZX, and you might get a ZX, like you need a ZX of, 365, but you're going to pick 378 because if you went off 365, you'd be picking the W24 by 131. Well, why don't you pick that one? It's lighter. Let's hit on your wallet. Does that make sense? Okay with that? Okay. Whew. Allergies are getting... Now what the... There we go. Yeah, we're done with the class. Okay, a couple other things. All right, so We've got moment covered and we've got shear covered. For now with shear, we're just going to look it up. What about deflection? Deflection's kind of funny because this is, I'd argue that this is the one problem, I don't say problem, but it's the one thing I have an issue with the steel manual in general. Okay? The concrete spec actually lists out deflection limits. Like it says, you will not design a structure that deflects more than this. And it actually specifies it. It's right there. The steel spec does not. Okay? If you go to chapter L of the spec, this is what it says on deflections. Deflections in structural members shall not impair the serviceability of the structure. And that's it. Not very much to go off of, is there? So the code does not actually specify deflection limits. Like in concrete design, we'd have deflection limits like L over 360 or L over 240 or something like that. The steel spec does not actually specify them. I wish that they did, but they don't. But a couple things. Number one, deflection shall not impair the serviceability of the structure. When you all took concrete design and we did deflections in concrete, what did we not do to those loads? We didn't factor them. We didn't factor them then. We don't factor them now. Deflections are not a safety concern in a building. If a beam deflects a little too much, it does not mean that if you put a feather, a little bit more load on the beam, that it explodes. Okay? It just means it's not performing its day-to-day intended function. So you do not factor loads. You only use service load. 1.2 dead plus 1.6 live. Just D plus L. Okay, so that's point one. Point two, just because the deflection limits are not in the manual does not mean that they are not available. One thing that I would suggest that everybody in this room do is go onto AISC's website and become a student member. Okay, I'm serious about that because one of the things that I think AISC does right, and I'll admit I truly believe I think they do this better than the concrete industry, is they make a lot of their design resources available online and available online for free. Okay, especially if you are a student. Okay, to become a student member is pretty straightforward. And once you become a student member, you get access to a number of design guides. These design guides cover things that we don't really cover in class, but you may see in your career. Like for instance, designing for torsion. Like we do our best to try and avoid torsion in a structural engineering setting, but sometimes it's unavoidable. We don't have time to talk about it in class, but that's where a design guide comes into play. Each one of these design guides, I want to say, is like somewhere between like $25 to $50. I'm really not sure, but there's like 30 of them. You get them for free, So I would register for these. One of the common ones, or very popular ones, is Design Guide 3. Design Guide 3 is serviceability design considerations for steel buildings, and it outlines a lot of suggested limits for deflections. In the steel industry, the limits have to be agreed upon between the owner, the architect, the engineer, etc. But there are a lot of suggestions in here. So for instance, these are some limits from Design Guide 3. So if you're looking at a non-plastered ceiling like this is a non-plastered ceiling. This is drop ceiling. You don't have that plaster on there. And we're talking about a floor beam. Our vertical deflection might be limited to L over 360 or 1 inch or what have you. In this case, under the dead load. A number of them are also limited to live load. For instance, if you're talking about a roof member, it might be half the live load on the roof or the 50-year snow, whatever's going to be important, or whatever's going to govern. I guess would be the best way of putting that. Sound good? But let me also say, ultimately, it is an agreement between the owner and the architect. In other words, if the owner and the architect come in and says, these beams can't deflect more than 1 inch under live load, well, that's what you're designing for. All right? Sound good? All right. My Claritin did this one. So for the purposes of what we do in here, if there are deflection limits to consider, I'm going to give them to you. Like I'm going to say live load deflection is limited to 1 inch, or dead load deflection is limited to this, or et cetera. Typically, they're a function of the live load. So Sound good? Now, if you find that deflection governs your design, you need to be designed. Hold on one second. If you find that deflection governs, if you find that you designed a beam based on moment and you find, well, it's deflecting too much, then instead of going to the ZX tables, go to the IX tables. Now, I've got here a tab marking on here. You probably don't need to tab this since it's right behind the ZX tables. Like if you turn a couple pages, it's right next to the ZX tables. Instead of organizing the shapes based on their ZX, it's organizing them based on their IX, their moment of inertia. So just like with the ZX tables, it's the same deal. They're broken up into chunks, and of these chunks, the one up top that's bolded is the lightest within the group, has the largest moment of inertia. Sound good?
Why are the limits typically a function of the load?
Okay. The reason that's a good question. The reason why deflection limits are more often than not typically a function of live load is because we can usually account for dead load deflection through things like camber. So for instance, if, let's say there's a floor beam supporting this load up here, and the dead weight of the floor is going to cause this beam to deflect 1/2 inch. I can take the beam and bend it upwards 1/2 inch so that when it's bent upwards 1/2 inch and I put the dead load on there, it sits flat. In other words, I can usually account for dead load deflection pretty easily. Live load deflection is a whole lot more variable. That's going to be a little tougher to account for in camber. Now think about this room. When this group leaves and the group comes in later, it's going to be a different set of loads, a different set of parameters. Does that make sense? What's that?
I'll be here next time.
You will leave after that. I appreciate your commitment to concrete and steel, though. That's cool stuff. Any questions, though? This is good stuff. I really want to make sure everybody's clear on this stuff. Are we good? Okay. I think I've done enough, going over a lot of the theory and the spec. I think it's time to get into some example problems. I think you're going to find that in practice, a lot of different design aids and a lot of different tables. I think you're going to find this is pretty simple. Okay. See if it's adequate. So, we have a 16 by 31 that's subjected to a dead load of 450 pounds per foot, not including its self-weight. We have a live load of 550 pounds per foot, and it's a 30-foot long beam that's simply supported. Now, we're going to calculate the moment capacity. We're going to look up the shear capacity, and we're also going to check to see if this beam, based on a service live load deflection limit of L/360. So let's sort of get into this. Let's take it one step at a time. I think you're going to find this is pretty straightforward. Okay. Get all this out of the way. Oh. I need to go to this slide. All right, let's start off with some structural analysis on this beam. Now, what is the dead load on the beam? Now, what is the self-weight? No? It's 31 pounds per foot. This one is picked. It's a W16 by 31. And a W16 by 31 weighs 31. Y'all remember this? Bringing it back, right? No, that's pretty much exact. And here's the thing. Let's say that you weren't sure. How would you find that out? You could take the area in the cross-sectional area in square inches, convert it into square feet, and multiply it by 490. See, remember to get the self-weight of a beam, take its gamma and multiply it times its area. So you could do that and tell me what you get, and you should get about 31 pounds per foot. Oh, you can do that. You asked the question. And this is 550? All right. All right, so tell me what to do. By now, you should know what to do with dead loads and live loads. We do for moment and shear, not for deflection. Not for deflection. Yeah. Well, why don't we do this? WU equals 1.2. Oh, come on. Okay, I think this is, you can handle this. I have faith in you, Mr. Fadiga. What do we got? 1457. We'll just keep it there. 1457. Do we have a second, Mr. Fadiga? Does anybody provide a second on this? Okay. Now, sir. Come on now. If you're panicking over dead loads and live loads, I'm wondering what like a horror movie would do. All right. Would it be fair to say this is 1.457 kips per foot? Okay. All right. Now, how do we get our factored moment? WL squared over 8. Which it is. How long is it, the beam? All right, and what does that come out to be? Say it again.
163.91.
Do I have a second on that? Okay. Now, what about the ultimate shear? How do we calculate factored shear, the maximum shear? It's a simply supported beam, uniformly distributed load. And what is the reaction? There we go. Now, if you didn't know that offhand, where would you look that up? Table 3-23. What does that come out to be? Say it again. All right. Now, before we call it, I do want you all to do something for me. So, just to make the point on shear, okay, I want you to go to the ZX tables. I want everybody to go to the ZX tables. I want you to find the W16 by 31. there is a possibility that it's not bolded. There's a possibility. Because we're analyzing, we're not designing. I'll tell you, it's not the case, but it is bolded. 16 by 31. Now, we're going to finish this example next time, but help me out. What is the moment capacity of this beam? 203. Is this beam good for moment capacity? What is the shear capacity? So it's a shear capacity of 131 kips, and it only has 20 kips on it in shear. That just happens with steel beams a lot. That the shear capacity is just through the roof compared to the moment capacity. That just is what it is. Okay? So far, just looking at this, does the beam meet moment capacity? Yes. Does it meet shear capacity? Yes. What about deflections? That's where next lecture comes in. We will finish this example next time. Then we will learn how to design continuously braced beams. Then after that, beam buckling. That's all I got.